Here we go.
This is lava. And this is also lava. One's man-made and one's, well, coughed up by Mother Earth. But both these scientists are working toward the exact same goal, figuring out how to predict the unpredictable.
To be able to make the best decisions about how to keep people safe, it's important to be able to predict what is lava going to do once it starts flowing out of the vent.
1/10 of the world's population lives within the danger zone of a lava flow, which means knowing how lava works and reacts to elements like water, metal, and ice is key. So, on this episode of Science Skills, we're going to look at 2 ways scientists study lava, starting with DIY.
This huge furnace behind me is Syracuse University's personal volcano and brainchild of an unlikely scientist and artist duo.
That's Professors Jeff Carson and Bob Vysotsky, and they didn't feel like waiting for a volcano to spit up lava. So they decided to make their own.
The project originated really when Bob came into my office and said he wanted to make lava. I thought that was pretty crazy, a suggestion at that time. But the more we talked, the more we saw that he had a really good idea of what needed to be done.
And the first thing that needed to be done? Figure out what to make the lava in, which is where this came in. The tilt furnace is really the statement piece of the whole operation. It can hold hundreds of kilos of lava and execute experiments about viscosity, morphology, structures, and formations. But she's a little bit finicky when it comes to lava making.
The furnace literally melts itself and tears itself apart over a very short period of time.
These were originally made to melt bronze and aluminum, but the Lava Project has repurposed one of them to melt up to 800 pounds of billion-year-old basaltic rock shipped all the way from Wisconsin. The process takes hours. Bob and his team pile the rocks into a receptacle called the crucible, turn up the furnace, and gradually bring the rocks up to temperature.
We were doing just lava and melting the stuff. Furnace would be on about medium, and we would just never turn it down or up.
What temperature?
It just runs. Medium is a sound out there that I hear the flame. I can adjust the furnace blindfolded and tell you what it's doing, and it's all sound. There's just a butterfly valve in here, and
Oh, you can hear it.
that's it.
We looked this up later. Medium is also somewhere between 2,000 and 2,400 degrees Fahrenheit. So pretty darn hot, which means these scientists really have to suit up. These suits made of aluminum can withstand radiant heat up to 3,000 degrees Fahrenheit.
We used to wear welding leathers, but it dries out from the heat. When you start to smell barbecue, because it's pig skin, you knew that you were too close to something because you're cooking, your clothing is cooking.
How do you know you're too close with these guys?
You don't.
You don't?
These are the spats, the apron, which I wear around my waist, the jacket, which, put your arms out, right? Because you don't need it in the back.
No. It's like
Right?
campfire style.
Exactly.
Back
and it's
heavy
just
is
that.
cool,
Yep.
that's warm.
So there's that, and then the helmet, it looks like it's a regular tinted thing like sunglasses, but this is 24 karat gold. That is this sheet of it.
What is
This
it
is
about
what
the
we're-
gold? Is it just the reflective
So
quality?
it's so
Yeah.
highly reflective, and it's why you see satellites and stuff. Why they have the,
yeah.
the gold foil on it.
And this is really similar to some of the stuff that like volcanologists would use in the field, right?
Same stuff.
Yeah, but maybe with a back.
They have a back on it.
Yeah, in case the volcano's behind them. Do you want to show us how it works?
Yeah.
go
Let's
see.
talk about this.
Do we need any of the gear? It is sweltering. How hot is it up here?
Well, the bright yellow you see back there, that's about 2,800 degrees Fahrenheit. So right now the lava in there is too hot. When we dump it out of here, it's about the meter it falls from the spout to the trough, and through the trough, we lose about 275 degrees Fahrenheit. By the time it hits the end, we want to be at 2150 Fahrenheit. And that's the magic spot for the lava.
Researchers are looking for that sweet spot between 1,600 and 2,200 degrees, the range for natural lava. Knowing the lava's temperature at what time and where is crucial. So the team has an array of 10 digital cameras to capture 3D images of the flow, and a thermal camera which can read up to 3,600 degrees Fahrenheit. That way, researchers like Ariana Soldati can analyze both the lava's movement and temperature, leading to a key piece of data.
Viscosity is possibly the most important property in volcanology. It really controls everything from eruptive style to appearance of the flow. And the main physical property that controls viscosity is temperature. The hotter something is, the less viscous it is, and the cooler it is, the more viscous. So it's really important that we can tell what temperature the lava is, because we want to match that with the viscosity.
With this, the team can study how different variables like metal or crystals affect how fast the lava cools and therefore its viscosity. But there's the lab, and then there's the real world, where unplanned and unpredictable factors come into play. That's where this guy comes in.
Well, this is a piece of the Earth that we call the mantle.
That's a piece of the mantle?
This is the piece of the mantle. And this is one of the sort of sidelights that makes some volcanoes incredibly important to study.
This is Ben Edwards, and he likes to get lava data straight from the source. Here's him collecting a sample from a flow in Russia back in 2013. As you can see, Ben's protective gear has more coverage than what they use at Syracuse, because sampling from a natural lava flow can be a 360-degree experience.
If you're going next to a lava river to sample, even in this suit, like I was doing this in Russia from a lava river that's maybe 10, 15 meters wide, and after being there for a minute or so, making some measurements, I could hear my Russian colleagues saying, "Ben, move back, you're smoking." But it was getting hot enough in the suit that even after about 30 to 45 seconds, I had to back up.
When Ben's around to witness an eruption, he's prepared to collect data. A lot of data.
Am I going to focus on taking lots of lava temperatures? Am I going to focus on getting lots of samples of lava? Am I going to focus on using drones and trying to map very carefully how fast the lava is coming out?
To pull a sample out of the flow, Ben usually uses a rock hammer. But
if I was trying to collect really hot samples, I would probably use some sort of an iron bar that wouldn't catch fire. Like this is okay for short.
It's made of wood.
Yeah.
Here's a clip of Ben's colleague, Alexander Belousov, using an iron bar to collect a sample.
He rests the bar on top of a rock and he uses a lever to pry the sample out because it's kind of non-intuitive. It's a lot stickier than it looks if you're just watching it flow by. It's like, wow, that must be pretty fluid because it's moving pretty fast.
That dollop of forbidden honey is then dunked into a bucket of water, not just to cool it down, but to cool it down fast because
as the sample cools, naturally it does produce these crystals.
The crystals, yeah.
And if you want to see what was in the sample as it was moving down the lava stream, then you want to cool it like that to kind of take all the heat out and basically turn the heat off so that you kind of preserve the sample. And you preserve the crystal content and the sizes of crystals that were actually in the active lava flow.
Crystal size impacts viscosity, so extra growth would lead to inaccurate measurements. To take the temperature of that flow, Ben might use a handheld FLIR camera, like Ariana did in the lab, or a 4-channel data logger.
Each one of these yellow things is a separate thermal probe. So with this recorder, I can record 4 temperatures at once. For example, if I'm interested in figuring out how fast the lava is cooling, right? So here's my lava surface. I might want to put one of these in, just barely in, and the other one I might want to have a little bit deeper. So I can put 2 of these together, and I'm measuring different temperatures now in that same cooling surface.
But you probably won't get those probes back.
I've got wires that are buried in Kamchatka because, once you get 2 feet of this underneath the lava flow, you're not going to get it back out.
That's not yours anymore.
No. It's one of the great things about the Syracuse Lava Lab, right? Because I do a lava flow there, and in the end I take my big hammer and I recover my equipment.
If you don't have probes to spare, you might try thermal mapping the flow from above.
And so drones are really revolutionizing what we can do to study active Earth processes.
You can strap a FLIR camera, a regular camera, or gas sensors to a drone. Potentially even all 3 if you get a drone big enough.
That basically become a volcano observation platform as opposed to just a drone. And one can envision even someday a drone that would have some sort of a tool that would hang down that would allow you to, if not sample lava, because it is tough to get your little sample bucket out. You wouldn't want your drone to get pulled into the lava flow. But you might be able to catch volcanic ash. You could hang a big piece of duct tape that's 20 feet long from the drone and fly it through a dilute ash cloud, and some of the ash particles would stick to the duct tape.
It's just like a fly trap.
Exactly.
But until robots officially take over, we'll need humans on the ground risking their lives and arm hairs to study lava flows.
You know, it's like the lava domes of Montserrat. The only reason we know there have been 3 or 4 domes, I can't remember which, is because there have been people watching and sampling. And yep, there's a dome, and then boom, oh, the dome blew away. Oh, there's another dome. Oh, then it blew, right? And if there wasn't someone there to watch, we might not necessarily know.
So it's important to be in the field for posterity?
Well, and for science, right? If we're trying to understand, that volcano and what it does over time to predict it in the future, and that's the challenge we face when we go to older volcanoes and try to understand what we see in the older volcanoes, because there was no one there watching.
Data gathered in the field helps shape safety plans for people in specific regions. But applying those learnings around the world would be almost impossible without careful testing in the lab.
As geologists, we always need that starting point of what happens in the field, what happens in reality. But unfortunately, in nature, there's no repeatability. Every time there's a lava flow, every time there's an eruption, it's going to be different. You have no control over any of the parameters. Here we can vary things in a systematic way, and this allows us to isolate what could be the cause and what could be the effect and tie them together.
Roasting marshmallows is an art form.
I would say it's a science.
All right.